Well, good afternoon, everyone. We are the Access Powers team, sponsored by Cobham, and we developed an inertial tracking system, and we will go into what that actually means. I am Anthony Islas, this is Jacob Berge, Jonathan Chua, and Christian Moncada. So, going forward, what is an inertial tracking system, or what do we mean by making an inertial tracking system? Because that could apply to a lot of things. So our project was meant to actually create two identical units in terms of hardware and software that would have a relative heading pointing to each other within a 3-degree tolerance. As you can see here, we had the ability to have an external marking in terms of specification requirements that would allow us to know an initial starting position, and then from there we would remove the units and they would still point to each other. So in terms of inertial tracking, we only were allowed to use an IMU, seen right here, whether it's a 6-degree or 9-degree. That was our only sensor that we could use for positional data, rather than using a GPS or ultrasound or anything like that. So what we're going to go over today is we're going to go over an introduction, so a brief system overview, key objectives that the system was supposed to meet. Some of the IMU threats, and so basically potential problems to the project that we're going to address, as well as our hardware choice analysis, some of the PCB design in terms of both what we had for development as well as what would go into production. And then into our software breakdown, we're going to talk about our modules and how we chose to lay out the software design, and then go into some of the design analysis and algorithm development, and then some of our outcomes that we believe were the most important highlights of our project. So for the system overview, I'll be taking over for that. So for our system goals, again, we had to develop a heading tracking system that uses inertial tracking, so our IMU, and it would use wireless communication, so we couldn't have any hard lines to the other units. We didn't have any tertiary unit, so no intermediate system where we would talk to a hub or a connecting device. So the systems had to have some way of detecting that there was another identical pair, and then pair with that one, and then send over its positional data gotten from the IMU. As for key objectives, we had to operate at 30 minutes without an external power source. So this was designed because Cobham wanted us to be mobile. And again, there were also requirements of having a dimension tolerance of 6 inches by 6 inches by 6 inches. So a very small handheld device that you could walk around with. Of course, we were actually operating only in 2 dimensions. It's because 3 dimensions is very hard to navigate in, and because of the extensive amount of errors that come in with an IMU that we will go into later, we wanted to actually stay in 2D and operate at that level. So while it might be handheld, most of our test procedures would actually be done on a flat level surface. And then we had to maintain that 3-degree tolerance heading display. So this goes into both the software internally as well as the display out to the user, because that's the most relevant information that the user actually has to see. That has to also be within the 3-degree tolerance. And then again, we had no other sensors allowed to detect the pair's location other than the IMU and the radio. So one for communication and sending over positional data, and one to actually track your internal positioning. So our system consisted of one unit inside a box. They were basically boxes. And the way we broke it down is we had this microcontroller unit, which was the centerpiece to everything. It was the brains of the operation. From there, we had the next most critical piece, and in terms of actual functional performance, this was the most important, and we will spend an extensive amount of time discussing that, is this IMU, where we receive data. So we get the raw data from our accelerometers, and we would transmit out any configuration information. As for the transceiver, which is the next most important part, where we would receive and transmit positional data back and forth between the units and go out in the airwaves. So in the power source right here, we actually had a 2-set system where we had a power regulator that was in between our microcontroller and the actual battery, that we wouldn't overcharge or anything. We had a regulator that regulated our lipo battery, and then from there you could power in and recharge your battery. And then all this relevant information that we've calculated would simply be written out and displayed on the TFT display and out to the display heading, which is, again, for the user, the whole reason for this. As for system construction, we had two main pieces. We had our development hardware, which we had somewhere over there. It's a stack that we had, where we actually got a bunch of perforated boards. We had that green one. And so we had the display on top, obviously, because you need to see the display, and then our IMU, our RF, and then connecting, so that way we would reroute the signals. This is mostly due to the fact that when you're developing, you have to get traces, do oscilloscope recordings, and make sure that you actually have connection to your device and you're sending out the right signals. While connecting at first to one device, it's very simple. You hook up all your wires, but afterwards it gets quite cumbersome connecting everything, reading in signals, and it gets pretty bad to the point where you don't know, you have to verify each time you go back to your lab space that all your wires are connected properly. And we've had this multiple times where we went in and something wasn't wired properly. So that was the main point of this, to just speed up development purposes. And we had the microcontroller unit and then the power regulator underneath with that battery. As for actual production use, we would go into a single board solution right here, where everything would be integrated onto one PCB substrate, and then we would have our battery or power source at the bottom. Now, integrating the CPU itself into one entire system would actually be quite hard and a project in of its own. So what we have designed later on, we'll show in our PCB development, is that we actually integrated the IMU and RF and some parts of the display, but not the CPU. That would be the next phase of actually going into production. And for IMU threads, Christian will be taking over.
Thank you. So the biggest problem with this project, and the reason it was so difficult, is because of the errors within the IMU. If we could just integrate the data, find out our orientation and our position, it would have been a piece of cake. But because of all these errors, the ones listed up here, it was a much more difficult task. The ones on the left-hand side that are highlighted in red are the ones that our algorithm accounted for and tried to compensate. Now, the ones on the left, in the left column, are all generic to any sensor, any IMU sensor, the gyroscope, the accelerometer, and the magnetometer. The static bias is the amount that's read even when you're standing still. So if you're standing still, it might read 2 degrees per second on the gyroscope, or a certain amount of G's on the accelerometer, even though it shouldn't be reading anything. And so that's what the static bias is. The bias stability is, over time, that bias will change. So if you leave it for half an hour, that bias might change by 1 degree per second or 2 degrees per second, depending on the quality of the IMU. The bias instability is, over time, throughout a year, every time you turn it off and on, that bias is going to be a little different. So it's not going to be exactly the same every time. Once again, the higher quality of the IMU, the more constant that's going to be. Below that, the misalignment is the error due to the non-orthogonality of the mounting of the sensors. So the X, Y, and Z axis are supposed to be orthogonal to each other and not interfere at all. However, due to manufacturing inaccuracies, it can cause a lot of errors and cause what's supposed to be a perfectly aligned system to not read fully what it's supposed to be. So as the Z-axis is aligned with gravity, it might not read the full extent of what the gravity is because of the misalignment. Below that, the cross-axis sensitivity is closely related, but if the sensors are perfectly aligned, there's still going to be some reading on the X and Y, even if it's only supposed to be read in the Z. And so that's what the cross-axis sensitivity is. The scale factor error is the error in conversion of the voltage read by the sensor into the actual units. So there is a conversion factor that's given with the IMU, whatever one you buy, saying this is what you multiply the value from the ADC by to get the degrees per second, G's, whatever you're reading. And there is a bit of error in that as well. So we had to compensate for that. And finally, the other one that is on that list is the temperature error. And so as the temperature fluctuates from differing from 25 degrees Celsius, which is room temperature, and the standard for most IMU calibrations is, as it differs from that, it will read it will get different readings. And so that's another issue. On the right-hand side, all these are specific to whatever sensor that it's listed under. The gyroscope has angle random walk, which is if you leave it sitting still, the amount of, and you integrate the signal, the noise in the signal will cause it to drift a bit. And so that is the angle random walk. And so over time, the longer you wait, the more that's going to drift. And the higher quality the IMU, the less noise, the less you're going to drift. And then the second one, sensitivity to G's. If you're moving in a straight line, you shouldn't be registering any rotation, but due to sensitivity to G's, you will still get something on that sensor. In accelerometer specific, the velocity random walk is very similar to the angle random walk, where it's the integration of the noise of the signal causing errors. But because to get position, which is what we want ultimately, the it's a double integration. So the single integration of that is the velocity. And so that's why we use velocity random walk as a metric for the quality of the IMU. And then for the magnetometer specific is the hard iron bias and soft iron biases. The hard iron bias is mainly caused by the ferrous metals within the environment of the sensor. And so whenever you turn a magnetometer in a 360-degree circle in the XY plane, you should get a circle in the readings whenever you graph them. However, with the origin at the at 0, 0. But the center of the circle, with hard iron biases, will be moved by a certain amount in the X and Y direction. So whenever you compensate for them, you have to subtract those X and Y hard iron biases to get back to the origin. Soft iron biases, because it's supposed to be a circle, the soft iron bias actually makes it an ellipse. And so to correct that, you need to have an ellipsoid fitting algorithm to plot the ellipse points onto a circle. And so these are some of the error sources and the reasons why this project is so hard for us. And so I'm going to give it over to Chua.
Thank you. So now that we went over the IMU, what hardware pieces did we actually pick? Well, first off, let me go over the system hardware diagram. We have the display, which we picked in Adafruit, and also going off, we picked a transceiver from Nordic, ARM Cortex TM4C launchpad from TI, an InvisionSense MPU 9250, the battery pack, and the LiPo battery itself. The battery and the IMU talk using the I2C protocol with the transceiver and the display using SPI because we want a faster communication rate between the two. So what the IMU we used was an MPU 9250 InvisionSense, which is a 9 degrees of freedom. The reason we chose this is because actually we worked with the MPU 9150, which is the precursor to that, and we have some experience with that. It was a low cost peripheral, but outperformed similarly priced IMUs. And as I said before, it's a TI supported driver library, which we have worked with in the past, and it's very well documented, and if we need any more help, we can go back to the community online and see where we made mistakes. And then the microcontroller that we used was a TM4C123. It's an ARM Cortex launchpad, similar to what we used before in one of our courses. So again, we have lots of experience with this microcontroller. And as I said before, similar with the IMU, we have lots of experiences with Texas Instruments. And it's very high, it has a high performance for the cost. It has 40 configurable pins, not all of which is used. So if in the future we want to add more peripherals, we're able to do so. And it allows the fidelity that we want with the data taken from the IMU with a 32-bit floating point position, and also has 80 megahertz CPU. And the radio that we picked was the Nordic transceiver, the 24L01. It's a low-powered 2.4 gigahertz transceiver, which actually allows us to use the 2.4 gigahertz broadband, which allows us to bypass the IEEE licensing issue. And it's also affordable for our budgets, and it allows for multiple system users. So it allows for multiple links instead of just having a one-to-one connection between individual units. And allows for 3 different operating modes, the 250 kilobytes, the 1 meg, and then 2 meg. So in case if we want to increase the units in the system, we could always bump it up if we need the required bandwidth. And then so for the screen, we picked a Adafruit display. It's a 128, 128 pixel resolution. The reason why this is so high is because one of our requirements was having a 3-degree of tolerance. And this pixel resolution allows for that sort of nuanced degrees between it. And going off that, the reason we picked an RGB is because in the future we want to have also in the Z direction and sort of mesh the vector with it. So we also have coloration showing if it's pointing up for red, down for green, and vice versa. And it allows, and it also is very cost effective for what we're getting. And the power supply is just simply a booster pack that we picked from TI. It allows for simple integration with the microcontroller just to snap in. And it's another TI instrument peripheral that we used. It's a 1200 milliamp hour LiPo battery, which supports 2.7 hours of operating time. Now this is with everything running and nothing on standby. So at worst case scenario, it's going to run at 2.5 hours, but it could even go further than that if some of the peripherals are on standby mode. And so that we have all these breakout boards, how do we integrate it? Well, we want to create a PCB to sort of mesh them all together. So this is the interconnect. Each one has a breakout to itself. The IMU is connected up there, all the radio, the display, and these pins are actually used for the reset button and the find button that we want to have. And the IMU simply connects in with the 40 pins that we have. And so overall, this is the breakout board that we created with the IMU up there again, the RF, the display up here, and the find buttons right there with the IMU, or the microcontroller right there. Note that we also do have a ground plane for the ground to connect it all and also help with RF transmissions, so it sort of filters that out a little bit. And we have holes, so we have standoffs, so it allows the attachment display very easily. And then the next step that we want to do is sort of integrate the entire breakout into one PCB using discrete ICs. And so this is how the general idea will be. This will be the IMU, followed by the RF, the display, and the find button there. This is ours, and this is just a whole bunch of mess of what we'll have to do in the future. Hence why there wasn't a board developed, because of the complexity of the schematic based on the skill level that we have. Because also we don't have a free version of Eagle, or we have a free version of Eagle, and the Eagle has a certain size that we have. It'll be too complex for what we could possibly do. And so now that we went over software, I'll pass it off to Jacob for software breakdown.
Okay, so for the initial software breakdown, we have kind of a 3-tier architecture for our software. The first tier is going to be kind of the application layer. Right below that, we have our actual driver layer. And finally, at the lowest level, we have our hardware bus layer. And the reason we did a 3-tiered architecture for our software design is because we can kind of drop in other components. The big one being the IMU. As Krish was talking about, the IMU that we have, there are a lot of errors that need to be calculated, and it just will not really be able to meet the spec that we need it to. So in the future, for dropping in a new IMU or a new screen, if that wants to be updated or anything, it's just we just need to update the driver layer of the actual software. And from there, the hardware bus layer and the application layer are going to stay exactly the same because they're abstracted in such a way that only the driver layer has to actually change. And next we're going to go over just kind of the modules that we have in our software. So we have kind of one corresponding module for each of our breakout board components. We have our power module, which corresponds to the battery pack. We have a display module, which corresponds to our display, a control module for the TM4C, a radio module, and then finally an IMU module. So the power module, it really just kind of continuously monitors the battery. It monitors the voltage, the current, the temperature, if it's charging or not, just all of the different variables with the battery, and feeds that back to the control module. And it also monitors the operating levels, if they're safe or not. So if we're over or under voltage, it can report that to the main control module, which can then act accordingly. The display module just provides the callbacks that we need for the different artifacts that we're going to display to the screen, which, as you can see, we display an arrow here in the middle, and also a battery gauge and a percentage of battery up in the top right corner of the screen. And another method of abstraction here is with the TI graphics library, which we use the screen driver to actually call the TI graphics library. So if another screen needed to be dropped in, it would just be a manner of abstracting that library again with the screen-specific code. Next is the main control module, which facilitates essentially all of the communication between the different modules. It's kind of the hub and the linchpin of the entire setup. And it handles just kind of all of the general initialization of the other modules, which at the very beginning of turning on the program, turning on the device, it just goes through and sets up all of the different components, and then goes into the continual running mode of gathering the data from the IMU and updating the heading. And it also manages the safe operation of those units, mainly the battery pack, which, as previously mentioned, if something's wrong, if the voltage is too high or too low, or the temperature's for some reason really high, the control module can adjust for that and either turn off or address the situation as necessary. Next is the radio module, which manages the receiving and transmitting of the change in positional data from the unit and also to the pair. And it also handles the find mode, which when initially pressed, the find button reaches out and finds the pair unit, and then they communicate with each other, determine a master unit and a slave unit, which then they can then transmit their changes in positional data to each other through the radio module. And it also implements we have collision avoidance with packet acknowledgement. So when the master unit or the slave unit sends data to the other, it receives a acknowledgement from the paired device, verifying that that device has actually received the updated positional data. And if that acknowledgement is not received, then it loops through a couple other iterations of transmitting the data and waiting for that acknowledgement until it's received. Or after, I believe, 3 iterations, it will just stop trying to send the data. And finally is the IMU module. So the IMU module reads calibration constants from memory, which some of them are calculated during the factory setup, or for us during our development phase, and they're stored in the EEPROM memory of the TM4C, and it reads those constants from memory for the initial setup and the initialization, and when we actually calculate our change in positional data. And it applies that raw data, or it applies those constants to the raw data that we receive from the IMU. And it also kind of integrates the calibrated data. So when we get in new accelerations from our accelerometer, it actually integrates those so we get a new positional change, and also updates our orientation. And it also tracks the pair unit as well. So while it's changing its own positional data and orientation data, the pair unit sends the other its positional and orientational data, and then gets updated within the internal data registers. And next I'm going to hand it off to Christian, and he's going to speak a little bit about the algorithm development.
Thank you. So the first part of our algorithm is the calibration step. As Jacob said, we calculate these constants beforehand. We do that so that we have better testing conditions. We can go to a rate table and turn at a specified degrees per second as the reference angular velocity to do our calibration with. We also can make sure that we're on a level surface and make sure that whatever axis we're currently calibrating is aligned with gravity. And also, because we do it, the user does not have to do it. And that means that every time the user starts it up, they don't have to turn it, they don't have to keep it still, they just have to turn it on, and it'll work. And so for our model, we used 3 sources of errors, the ones that were highlighted in red earlier. the static bias, the misalignment, and the scale factor error. This equation down here is the model that we based our calibration off of. Right here, these f sub x, y, and z are the actual what we should be reading. So if we're aligned with gravity, we should be reading 1g on the z-axis and nothing on the other two. However, what we actually get is this f with the tilde above it. That is the approximate what our sensor is reading. These other matrices are the errors, the sources of errors that we are accounting for. The B terms are the biases, the static biases, and that's why they're just added. Since they're static and they aren't scaling with what we are reading, it's just we just add it. This matrix is the scale factor and misalignment matrix. The M terms are the misalignment, and the S terms are the scale factor. So whenever you multiply the scale factor and misalignment by the by the actual readings, you get a skewed sense of what you should actually be getting. So whenever to go backwards and try and get as close as we can to the actual readings, we inverse this. So we take the f tilde and subtract that bias from it, and then multiply by the inverse of the misalignment and scale factor matrix. And by doing that, we get much closer to what the actual readings would be. Right here is some test data that shows how effective our calibrations are. On the left-hand side, you see the uncalibrated. On the right-hand side, you see the calibrated for acceleration data over 10 seconds. So if you look at the second and third graphs, there are velocity and our position. If you notice, in the uncalibrated position, we go up to almost 20 meters on the y-axis. Whereas on the calibrated position, we only go to -2 on the x. That's almost a tenth of what our original error was. So if you look at this graph, this is the overall position that we've moved. So the magnitude of the position vector for the calibrated and uncalibrated data. As you can see, we moved much less with our calibrated data. And so even though this is not good enough to reach our spec, it's a good start, and we would try and get better calibration data and apply more complex algorithms to correct more of this data and get us closer to what we need to be at. So after the Excel and MAG calibration, Excel and gyro calibration, we have the MAG calibration. It's a little bit different because we can't align perfectly with the Earth's magnetic field as a reference frame. We only do hard iron and soft iron bias correction. This is okay because the hard iron biases are going to have a much greater effect than the other types of error, just due to the nature of magnetometers. This graph is an example of what a magnetometer measurement with a hard iron bias will look like. If you notice, it's in a perfect circle, but the origin of that circle is not on the origin, or the center of the circle is not on the origin of the graph. So what the hard iron calibration does is it takes that circle, moves all the points so that the center of the circle is at the origin of the graph. And by doing that, we get a much more accurate magnetometer reading. And so once the calibration is done, we have our initialization step. And so with our initialization, the first part is just to initialize all of the values. And so these values include the positions, which will start at 0, and this will start during pairing, so that the initial position at pairing will be the local origin for that unit. And so whenever it tracks its positional data, it'll track it in the global frame with the center at 0. And what I mean by the global frame is north being the x-axis, and then gravity being the z-axis. And so with that reference frame in mind, both of the units in a pair can have a similar reference system. So whenever they say, I'm moving in the X direction, the other one knows it's, whenever it adds it to the X direction, it's adding to the same X direction. So they have a similar reference frame to go by. And so to calculate the initial orientation in this global reference frame, you use the magnetometers. And that's this equation down at the bottom right here. Theta is the orientation, the degrees off from north, and the y and x are the magnetometer readings from the x and y axes. And so with this a tan 2, it calculates the angle that we are off from north. And since we are only in a 2D space, all we need to worry about is the x and y axes, because we're in the xy plane. And so this is an example of what the initialization step would look like. First, 2 units would pair, and they would have their own reference frames that, and a global reference frame. As you notice, as they move away, they keep their own body reference frames, but the right-hand unit spins and has a different body frame, but it still uses the global reference frame to talk to its partner. And so during runtime is whenever we do those things. So the first step is to update the orientation. And so to update the orientation, we use both gyroscope and magnetometer values. Since the gyroscope is reliable over a shorter period of time, it's very accurate, but the magnetometer is more reliable over a long period of time, we wanted to get the best of both worlds. So we calculated each estimation separately and then combined them. So for the magnetometer, we just used that equation from before and calculated a new orientation based off of that. With the gyroscope, we integrated the reading and then added it to the previous orientation to calculate the new orientation. Then once we had those two, then we used the simple complementary filter, the equation right here, to calculate the new one. The sigmas are the amount of, is a measure of the reliability of a sensor. So it's the expected error that we have from it. So the greater the expected error, the lower the weight that it should be. Now over time, since we said the gyroscope is going to get less and less reliable, the weight for the gyro is going to get less and less, whereas the magnetometer is going to stay constant. And because of that, it will make sure that the magnetometer is trusted more as time goes on and give us a more reliable reading. So once that orientation update is complete, then we move on to the position update. And the first step of the position update is to rotate the accelerometer data into the global reference frame so that both units are tracking their position in the same reference frame. And so to do that, since we're only in 2 dimensions, we use this rotation matrix. And so whenever you multiply that rotation matrix by the x and y accelerometer data, you get x and y accelerometer data in the global frame. And then once that's rotated, we do a time step integration. We're running at 100 hertz, so every 10 milliseconds we're doing this integration. And so we integrate the rotated accelerometer data to find the new position, and then we integrate it to find the new velocity. And to do this, we just use the simple high school physics acceleration and position equations. And so this is a data flow diagram representing how the data would flow in the system during this IMU runtime process. So we start with the time step, and from there we get data from the IMU, and then apply that calibration in this process raw data step, and then move on and we update the internal velocity and update the internal position of the unit. Move on to the position data, which combines the internal of the unit itself and what we get from the radio to update the pair's position. And so that's stored in our position data variables. And so from there, we pass those readings into a calculate heading function, which then displays that to the screen. And the calculate heading function just takes the 2 points, the unit's position and its pair's position, calculates the orientation, the heading between the two, and then gives that to the display driver to draw on the screen. And so I'm going to give it over to Anthony to finish up with outcomes.
Thank you. All right, so as Jacob, Jonathan, and Christian went over, we had a significant amount of work to do in the project, but overall, we actually significantly increased our IMU calibration and analysis to our readings. If you saw on that graph, that we got our readings down from an instability or a position reading of almost 20 meters after 10 seconds to about 2 meters. While again, as Christian noted, that this would make us fall out of our specification of 3 degrees per second, or 3 degrees after 30 minutes. It's a good step forward into where we would want to be. And we also developed IMU analysis on where we would go next. So how the specification of an IMU and all those biases and errors, because some of them we can't actually fix ourselves. They are inherently inside the IMU, and thus we need to either do calibration readings and do tests on them in our factory or production line, as well as the next biggest step, which would be to get more funding and purchase a better IMU. Because ultimately, no matter how much we do, we can't get rid of these errors. So the MPU 9250 that we decided that we would use, while a good start into the project, and especially great for our budget, will not satisfy what we need for our key objectives. So instead, we found what IMU selections we would go for and what would be viable in terms of the next phase of production. Next, we also created our modular design. While this is a proprietarian, it's actually a very good design in terms of how we laid out our software. This means that when we pass it on to, let's say, another Capstone team that would pick up from where we left off in the following years, they could use our modular design, and for instance, let's say they get some more funding and actually do purchase a new IMU, the device driver would actually be significantly different, but we would only need to replace, as Jacob had talked about, that device driver layer and then drop in that device, and as long as you're using the same bus protocols and the same API format, it would flow in seamlessly and we wouldn't need to change too much of the actual underlying architecture or the logical flow of the software. And then from there, again, going back to if we had new Capstone teams come in and pick up where we left off, we had actual use of CMVC and so control management and version control of software. So if a team were to come in and see what we had done and any modifications we've made to the software, how we divided up the tasks or the modules, any changes that we made that potentially we don't know as we went into testing that we broke something, a future team could come in and see where we messed up or any changes that we made and then go through with that and potentially build off of our current project and have tracking in that. So overall, those were the biggest things that we were able to create. Again, mostly focusing on that IMU analysis and a good source or a good direction on where we want to go if we had more time and funding for this project. So overall, that is the conclusion of our presentation, and I don't see any Cobham people here, but we'd still like to give a special thanks to our sponsors. And that is our poster that was out there. Do we have any questions? I'm sure we do.
Hello, my name is Oleg Cindy. I apologize for the delay coming in here. Stuck in another presentation there right now, but I wanted to give you guys say I've really enjoyed your use of equations and explanations what they meant. It really made me understand that you understood the fundamentals. I also really appreciate that you guys identified the sources of error. In industry, often when we get stuck with these kind of what you guys end up being in is called a technology risk reduction effort, where you have a technology that's critical to your larger effort that you're trying to do, and you end up kind of you have to invest in this technology to reduce the risk and make it meet your needs. So it's very much a real thing that happens, that sometimes these things that you think, oh, they're fine, you have to invest money into reducing the risk and making the technology work for you. And by the way, just from the theme of all these presentations today, manufacturers are very much will overstate their performance capabilities, and by pretty much I say will always overstate. So there's an industry, there's a whole group of folks called quality assurance and parts inspection that will have to take the parts that have been received and test them and see whether they meet the specs, and oftentimes they'll have to send back. So you And if you're counting in that, you have to account for that in your time and your budget, that you might have to wait for that manufacturer, or sometimes have to do it yourself because you can't get anybody to do it right for you. Or sometimes it's infeasible, or maybe the technology is not ready yet. And IMUs seem to be a guilty party all around today. So if if it's anybody's fault today, it seems like all projects really struggle with the IMUs. So you guys hit the nail on the head there. Question that I have for you: are you at all worried about the computational loading with all these mentioned modules and calculations that you have to do? Do you think your system will be able to handle all these calculations when they're running together?
Thus far, with what we're actually doing, I don't see a problem with that. We actually were working on the next phase in terms of our integration and actually having so we had that time step, which is the most critical part where we have to dedicate actual cycles. So we're actually going to use a system clock tick. That way it had the highest priority in terms of interrupts. But otherwise than that, we're going to revise our specification where we had the display refresh rate at about 15 hertz. And it didn't make sense that if we weren't moving, then why update it? Instead, just have those idle CPU cycles used potentially somewhere else. And again, we mentioned that our IMU or our MCU can operate at 80 megahertz. Thus far, it hasn't proven a problem, but we do see later on in the future where we would actually try to meet that specification, and we're getting our data from the IMU, and then also having time slices dedicated to transmitting on the transceiver. We would potentially move to something a bit more powerful.
Okay, but at least you've thought about the issue and keep track of it. That's good. Computational power can be you can run right into it and have to change real quick. A couple of items on the presentation. A few times I think the font text might have been a little too small, so make sure, test it having somebody who's really blind stand in the back and see that they can read every slide. As well as, I think more importantly, is some folks are colorblind, or if they print out your charts in black and white, and some of your graphs I noticed that you use just a red and blue line, and if somebody's colorblind, they won't be able to tell the difference, and so you just lost. If you're presenting to a key customer and they can't tell what the plots mean, you just really shot yourself in the foot, and it's an easy problem to fix. Use something like a dash line or circles, triangles. So that's a really neat little trick to keep in mind when you're creating plots and making sure that you don't lose any of your audience members there. Let's see. I think. Really good use of accounting for drift through I really like your innovative solution that you kind of came up with. Use the accounting of drift through time-changing weighted function. I really think that's pretty cool. So I don't know if you guys came up with the idea, or the professor helped you, but I'm really impressed.
Yeah, Professor Bruder mostly helped with that.
So he's a smart guy then.
Yeah.
But that's a lesson learned that use your technical experts, use your resources, and a lot of times that resources in industry are the other people, folks that are smarter than us that have gone through these through these growing pains. But I was really impressed with that particular application. So good job, guys.
Don't need the microphone, Dr. Davis?
No, I don't need the microphone. So this is the second time I've seen this today, and I noticed you changed a few slides in the interim. If you had to give advice to the next team here, what kind of advice would you give to a team that was going to pick up this project and try to commercialize it?
I would think, I guess I'll pass this around after I'm done, so each one of us gets a little pick at it. I think first and foremost would be try to get a larger budget, because evidently that is the highest cost. If not, if you still have to stick with the MPU, which isn't a terrible IMU for its cost, I would say learn the scope of the project, really focus on hitting those deadlines, because ultimately 90% of the time you have hardware issues where you just can't connect, it's finicky, and one day it's working and one day it's not. Overall, I think we developed mostly robust drivers, but I think a lot of time should be spent more on making sure that the actual system altogether works, and making sure that that you actually decide at an early stage what the API is. So I'm going to provide you with this information, this is all you need, and this is how you're going to call it. We had some of that mostly figured out, but when it came down to much more of the higher technical aspects, such as deciding on how we're going to do positional data, whether we're going to do a local origin or if we're going to do a global frame, that was kind of up in there until we actually had to get to it, and it proved kind of cumbersome in terms of modifying our algorithms to revolve around that. So I think first getting an outline of how do you want your design to actually be, and then making sure everyone agrees on that, and everyone knows that we're going to go to this one point, because again, as you heard at COB and when we were presenting to them, you have these requirements, and then everyone interprets them differently, and you all go out into your different directions, and it takes 5 times as much time to come back to that one single point where you actually meant to be. So I guess overall, clarifying your design and also making sure you have well-defined specification requirements.
I would say for specifically this project is to get the math equations first and like understand the math equations, because if you don't understand the math equations and you try and implement them in code, it's going to turn out wrong and you're going to get very frustrated. So learn the math, know what the math does and what every variable and constant means, and then move forward and say, this is going to be much harder than I thought to implement in code. I need to spend more time on this than on this. And I think during the planning stage, if I had spent more time on the actual algorithm and learning why is this problem so hard, rather than, what hardware should I use, I think it would have turned out much better.
I would say for this project, but also just projects in general, allocate extra time for potential errors or things that come up that you don't necessarily expect. Like as was said, companies over-exaggerating for either their like statics or statistics on certain parts, but also some companies will say they have a complete like driver library and this piece is just drop in and it doesn't work at all, so you have to redesign everything. So just allocating extra time for the inevitable setbacks that are going to happen.
And it's already been touched upon a lot, but definitely sticking with the project management, breaking down each component and having set completion dates and sticking with it to the teeth. Because if you push back a part of the critical path, then it sets back everything. And then waiting on one piece while someone else is done sort of messes up the whole Gantt chart itself. And so my biggest advice is make sure you modularize each project or each module properly and stick with it and make sure you meet the deadlines.
Another thing I didn't interpret what Jacob said is code reuse does not mean you will save time.
You got it. Yeah, it's very good. Like quite a bit. On your IMUs, you showed some errors. I was curious, what was the original objective? I'm a little bit behind here on understanding the goal and what is the final deliverable. You showed some arrows too as well. The arrows were tracking each other. In your display of the results, I was curious how well you really obtained those results. Is there any comment on how close you were to your original objectives on this?
Yeah. So the system that we're planning to make is these two, it's really finicky. There's something wrong with it. These two units that would basically be identical and kind of stay idle for the most part. And then there would be a find button, and then once that find button would be pressed, and both being pressed at a simultaneous time, or roughly, they would go into this find mode for a given duration. From there, they would actually pair, and then if you turn sideways, so that you can see the screen. Yeah, they would actually, when powered on, they would have an arrow pointing to each other. So they would basically have that local origin that we created. Let's go back to that. So right here, so those boxes, while they don't show the display on them, they would actually have that display on the top, and then in that very first slide that we showed, they would have that arrow and then continuously point to each other's position. So it would be more of and the underlying part of it is that's mostly a position tracking, but overall what we display to the user is heading tracking.
Okay, so you mentioned the error, so you showed like a 10 to 20x improvement from a non-calibrated. Is the objective to get, you mentioned how much better do you need to have a real project here?
Well,
Do you want to go into the actual website with the IMU comparisons? It's right there.
where'd you put it?
On the right. Very first one.
Yeah, so this is our comparison of IMUs. This is just the Z gyroscope, what the orientation reading would be, sitting still for 30 minutes, what it would be. And as you can see, the MPU with no calibration, with just these 4 sources of error, the 2 in red, we calculated ourselves, is 90 degrees, which is pretty far off. And we have to be within 3 degrees. And this is just the Z gyroscope and not the accelerometers and tracking the position, integrating the position based on our orientation and all of those other sources of errors. So to get that degree of accuracy, we would need the root sum square, the RSS, to be less than 3. And so that's the error with the position of the IMU, or the position of the system, has to be within a certain amount, and along with the orientation of itself being within a certain amount, squared and summed together, and then the root of that has to be under 3 degrees. So this is our just Z gyroscope, the only one uncalibrated, the only MEMS IMU uncalibrated that we found that would fit our spec is the STM 300, which is about 10 grand. So we need a bit more of a budget.
So at the end, you did this analysis looking at one axis, right? And your problem was 2 dimensions of position and orientation. So at least it gets a little worse.
Yeah.
Is there anything else you can do other than throw money at the problem? Are there any other ways that you can think of to try and address the performance gap?
Well, some of the other things is like adding temperature correction. A lot of data sheets will come with a degree or a change per degree in Celsius that you can apply. But the change isn't linear like the data sheet would have you believe. Some companies go up to a 3rd degree polynomial model for what the temperature, how the temperature affects the IMU, and so that would be the next step, is applying at least a 1st degree polynomial using the data sheet values. Possibly from there, collecting data over multiple temperatures and calculating our own 2nd, 3rd degree polynomials. To reduce noise, Kalman filters are good at that, but that was a lot more math than we were ready to do for the scope of our project, just because we had, mostly because we had a lot of hardware problems and we didn't get to do a lot of math because of that. And so that would be one of the next steps, is researching more on Kalman filters and how we would apply them to our system to reduce, and that would help quite a bit. Applying soft iron and hard iron biases. I went over the hard iron biases because that would be the immediate next step of what we would do, but the hard and soft iron biases would probably be, along with temperature, the next 2-3 things that we would apply to improve that performance.
Maybe a bit of a follow-on to that, to the wider audience, jump in as you. If you were to relax the requirements a little bit, could you think of any other kind of sensor that wouldn't necessarily blow the budget, but get you closer?
I would definitely include a GPS. It would definitely make things a bit easier, but again, that would be relaxing the requirements significantly because our operating distance is actually within 30 feet. So if we had the ability to go between a certain range, so more of a disk range, let's say between 30 to 50 feet, the degree of heading tolerance could actually be relaxed a bit more, or in terms of the actual position and distance, because at the closest that we were together, to get a 3-degree tolerance, we only had a few millimeters that we could be off when we were pairing. And so one of the hardest tests that we would have done in our test procedures is simply having the boxes paired and letting them sit there and letting the drift go. And as it's the closest, any deviation in the position, it would create a much larger change. But if we operated at a further distance, we could actually use a GPS with fairly decent accuracy and then use that in relation with the IMU as well.
Did you try reaching out to the vendor to see if why your results were so different than what they were advertising?
For the MPU, they actually didn't give us the Ingaranamoc or this bias stability, so I just had to calculate those myself out of necessity more than datasheet values. Most of the other ones were explicitly stated as a 1 sigma above mean for the results of those values. So that's why the MPU looks a little better here, because we calculated those values ourselves, so it might have been much closer to a mean value rather than a standard deviation above, or even better than the mean for their products. But for the most part, as we increase the quality of the IMU, the overall drift is diminished quite greatly. And with how much tolerance we have, every little bit counts.
Okay. What about reaching out to the other vendors to see if they were give you the poor starving college student discount, which is usually, can you give me a sensor or two for free?
Yeah. By the time we realized that the MPU would not work, it was already too late into the semester. We only had, say, a month left, and getting that sensor, waiting for it to ship, getting the driver working, and then implementing all of that stuff would have put us behind in doing this research, in doing furthering our algorithm, getting the other parts of the system to work, like the display and the radio. And so we just decided that it was too late in the semester to begin that. If this were an actual project and we had another 6 months, we would say, okay, we have time, like this isn't going to work, we need to get a new IMU as fast as we can.
Any other questions from the audience? Okay. Thank you very much.